Okay, welcome everybody for the afternoon session of the last day of the electric workshop. And I'm happy to present Koroteev, who will speak about quantum geometry, integrability, and Opers.
Thank you very much. So I'd like to thank the organizers for bringing us to this beautiful country. It's haven't been to Japan since the pandemic, and yeah, I'm really happy here. And I already made this joke on the internet that elliptic conferences happen every 4 years. It's like an Olympic Games or a World Soccer Cup or something like that.
They happen every 3 years, it's just to keep getting hooked up.
Oh, okay. Actually, yeah, with Slava we had this online workshop last year and the year before, so I will try to fill the gap. Okay, so so I'll be talking about things that some of the stuff I'll be talking about was already discussed earlier today, this morning by Andre and by Richard, but I'll give some different perspective on this. In particular, I'll try to demystify this word Opers. What does it mean and why is it a natural object to study in this business? So, kind of motivation comes from various angles here, including physics, universal geometry, integrable systems. So, in string theory, people have been studying for a long time, various setups where there's a strong connection between geometry and integrability. So, in particular, Gromov-Witten invariants, study of those were influenced by, well, obviously by string theory. So, if you have a symplectic target X, then GW invariants appear in the expansion of the quantum multiplication, quantum cohomology of X. And particularly, people work a lot in genus-zero Gromov-Witten invariants. And then today, we'll go from cohomology to K-theory and even beyond to elliptic cohomology. So, we'll study equivariant. Primarily, we're working on equivariant quantum K-theory of large Hamilton spaces like field varieties, and we'll discuss their connection with quantum integrable systems, which are described by beta ansatz, and classical integrable systems like Kalodner or Rosinars, so those models that everybody in this room know and love, and how all these integrable systems come up in the study of in representation theory. So representation theory, algebraic geometry, all the things that come together. So this is famous last board of Richard Feynman in Caltech, right? And you can see here, so he on top, he says to learn, right? It says beta ansatz problems, right? And then it's actually quite fun to read this whole board. Like next line it says Kondo, it's the sort of condensed problem. I look like he crossed it out, like Richard Feynman learned Kondo problem. Good for you, Richard Feynman. And then actually quantum Hall effect and so on. And then like the top left box here says, what I cannot create, I do not understand. And the box below says, know how to solve every problem that have been solved. Because towards the end of one's career, people become more philosophical, but it certainly there's a lot of we can understand from this board. And independently, he said this also towards the end of his career. Then I got really fascinated by these 1 + 1 dimensional models that are solved by beta ansatz, and how mysteriously they jump out at you and work, and you do not know why. So I'm trying to understand this better. So my research is very much in line with the statements. I'm trying to understand them better, geometrically, representation theoretically, and what else can be learned in this story. Okay, so let's begin. Let's quick review of many body systems. So Kalodner in 71 introduced this new integrable system, well, it was new at the time, and then in 75, Moser proved that integrability using Lax pair. Right, so in the kind of simple setup with open boundary conditions, we have coordinates x1 to xn, right, and then the Hamiltonian is a sum of the kinetic term, and then coupling constant g times the potential, which is the pairwise interaction. Then you can deform it in various ways. You can have periodic boundary conditions, and you can change. Yeah, so that will change the potential. So you can have rational, trigonometric, or hyperbolic. But for me, everything will be complex algebraic. So it doesn't really. I'm not distinguishing between hyperbolic and trigonometric. And then there's the loop. Okay, and then another generalization was done by Rosinars and Schneider. So you have to So instead of having a kind of differential operator, you get the difference operator. And then again, there's a hierarchy: a rational RS model, trigonometric RS, and elliptic RS. And then, like, if you take this speed of light to infinity limit and subtract the rest mass energy, then you'll get a Calder system. Right? I think I give this exercise when I teach calculus, when I talk about limits. I give this limit, just calculate this. See if you've seen this before. So an example of, in the context of K-theory, as we know from talks before, that is the TRS model is the most relevant one. So here's a lightning review of the TRS system for two particles. So there are two Hamiltonians, which I call them T1 and T2. So psi1 and psi2 are the coordinates, P1 and P2 are conjugate momenta, and then you can see that the symplectic form is, it's a log symplectic, right? So like we should think of those T and C as exponentials, right? And so the integrals of motion here, you just said well, classically have some energy levels, so Ti is equal to I, with some Poisson bracket, which is induced by the symplectic form, the Poisson commute, right? And then when you quantize it, you have, well, this quantum torus relation with a quantum parameter Q, right? And then those TRS Hamiltonians, they become shift operators, right? And you can study their spectrum. And in particular, eigenvalues equations, which we'll see at some point soon. So you see here that the coordinates, there are this coupling constant T, and there are energies, and all of these quantities will play a role in enumerative setup and later representation here. So in general, the construction goes as follows. It is for this type of model. So you have so you define so-called Cauchy-Moser space, which is certain stack quotient, but roughly speaking, it goes like this. So you have an n-dimensional vector space, complex vector space, and then you look at M prime, which is a subset of GLV cross GLV cross V cross V dual, which consists of a tuple, two matrices and two vectors, or the vector and covector, which obey this kind of relation, which reminds kind of the Q commutator of matrices equals to matrix of rank 1. Right? And then modular simultaneous conjugation by element from GLV, right? So if you take equivalence classes to modular this conjugation, you'll get what is known as the Cauchy-Moser space. Then there's an independent formulation in terms of local system on a punctured torus. You take a character variety of the torus with one puncture, and then you select the monitor where that puncture has one distinct eigenvalue, right? And that eigenvalue is equal to T, the coupling constant of the Rosiner system. And then in this latter case, the relationship between the monodromes A, B, and C is just the fundamental group relation of the punctured torus. So we discussed this paper yesterday in the context of Shamil talks and others. So in this paper, we study this in great detail and understand representation theory of Daha and rank 1 in connection with the Fukaya category of this space, and it's a beautiful story. I'm not going to be talking about today, but it's very much related. And then, so the classical Hamiltonians appear from, so you compute this matrix T, and you compute its traces of various powers of T, and those will be, so T will become what's called the Lax matrix of the Calder system, or the RS system, and then its Casimirs will give you Hamiltonians which commute. So we have this is the table, we've seen this before, so you can have this 3x3 table with rational trigonometric and elliptic models and coordinates and momenta. So the king of the mountain is Del, right? He sits on top of Mount Fuji, right? And you can sort of go down to elliptic RS and then to this dual one, and kind of it's still work in progress. So with Shamil we have conjectures about the Hamiltonians, and we're sure that they work. It's just a matter of proving that it is to prove those conjectures. So we have expressions for Del Hamiltonians, and then we checked in some orders in expansion that they commute, and we'll have the eigenvalue equation as well. Okay, so essentially, and then what I want to say is that every model in this table has some kind of geometric or algebraic meaning. it's really remarkable. So you can relate L-algebra series with cohomology theory, elliptic resonance series with K theory, and then this bottom line with elliptic cohomology. So so these were classical integral systems. Now let's talk about quantum systems. This is a light review of this 40 plus years, or maybe more, of development, right, by Japanese school, by the Soviet school, and by others. So this treatment comes from Rishetikhin, Fadeev, as well as Jim Blamiva. So we can think of a quantum group, this UH bar of G hat, as a non-commutative deformation of the loop group, right? So simply, it's so we have the algebra G, right? You can have Lorentz series or Lorentz polynomials valued in G, right? And then it's a certain deformation of that thing, right? With a non-trivial intertwiner, which is called the R matrix, Beard and Smirnov stocks and others. So just think of it as this intertwining operator between two representations with relation parameters A1 and A2, right? So that's like a evaluation representation of this algebra. It depends on the loop variable, and you evaluate it at some points, and then there's a certain linear operator like this, right? And then essentially you can just bootstrap it. You can say, okay, our matrix satisfies its operator of this form, and it should satisfy this Yang-Baxter equation. And like with minimal requirements, you can essentially find it, right? Which is just from symmetries, right? So then integrability, quantum integrability comes from the transfer matrices, which generates a called beta algebra. So you take so it's like you consider the trace, our matrix sort of intertwines two representations, and then you trace out one of them, and maybe sort of insert this twist operator Z, right? And yeah, so trace over this W space, which is called auxiliary space, and then the resulting operator will be a matrix, right? It goes to this kind of one line coming in, one line coming out, and it commutes the different values of this loop parameter, right? And the quantum integrability follows from here because each of them is a polynomial in U, right? And that encodes, that tells you that a bunch of coefficients can commute to each other. So those are integrals of motion. And then, yeah, so physicists have their own way to think about this. There's this omega background that allows you to kind of quantize classical systems, right? Using methods of gauge theory. Sort of more formal aspects are formal ways of sort of quantization by branes, by Kukov and Witten, and that's the formalism that we use in the Dama paper that I mentioned. Now, I want to talk a little bit more about this, and then we'll come to enumerative geometry in a second. So consider what's called the XX15 shape, right? It's kind of the example of the quantum system that I'm considering, and take the G to be SL2, right? And then consider this module of the loop algebra of SL2, where you just take the tensor product of those fundamental representations, which are induced from the fundamental representations. So you just say the C2 of A1, tensor, and so on, C2 of AM. And you consider what is called a Q monodromy around one of those simulation parameters. And that leads you to the quantum fission homology equation, right? So here's the cartoon. So you take one of those vector space, and you intertwine it around, loop back around, and then again insert this twist operator, and then you come back. So on one side you've done the Q monodromy, on the other you acted with this product of R matrices with a twist on your wave function, right? And then if you send Q to 1 carefully, then this will become an eigenvalue problem. Right? And you can ask what are the eigenvalues of this KZ Hamiltonian. So, people have been studying these KZ equations for quite some time, including Vitaly, Satarasov, Harchenko, Mukhin, and the Japanese group, everybody here. So I'm really kind of come into this quite recently. And roughly speaking, the solution looks like this. So there is the size of alpha. So if alpha indexed by this physical space, right, which is one of those evaluation modules, right, then it's certain complex interval over some contour of there's a universal kernel, right, which is described, which has described by the algebra, And then there's a and you take a convolution of this kernel with this representation with a certain function that is labeled by, well, in this by physical space and by the representation. And then this kernel, its saddle point approximation gives you this function of x, z, and a, right? So z's are the, if you wish, well, okay, this will come in a second. So a is seen before, but these are what will become Halo parameters in the Q variety. Well, sorry, no. So these are the eigenvalues of the three-step rate. Right? So if capital Z has eigenvalues little z, then they will appear in the kernel, right? Okay, so how do we find those functions? Well, so first of all, if we do the variation, like the variation principle for this function s over those integration variable x, you'll get some equations that are called beta equations, and x's are called beta roots, so terminology. And then the log derivative with respect to this relation parameters, given let's call them lambda, those in fact are eigenvalues of the Kizzy operators, right? So of the Kizzy Hamiltonian. And kind of if you think about this formula, what it effectively does, it provides the kind of diagonalization from the kind of space of those initial space of representations, right, of the spin chain to this it sort of provides the diagonalization of the QKZ Hamiltonian, right? So like in this basis f alpha of x star, right, the Hamiltonian x diagonally, right, and you can find exactly that. Those are eigenvalues lambda. But the caveat is that you need to solve these beta equations, right? Plug in solutions inside, that's why it's called x star, it's kind of on-shell solution, and then you have solved it. But the challenge is still to find these off-shell beta functions, like what are they and how to understand them. Right, and this is where the enumerative geometry comes in. So it's kind of the mathematical construction which is heavily based on physics inside by Statistical Gentleman, Nekrasov and Chitashvili. So essentially the idea is that the Hilbert space of states of a quantum integrable system like spin chain or many others, in this case, if it's XXZ chain, you can map it to the equivariant K-theory of the Q variety. Right, and then my favorite example by far, it's not my favorite space, is Koroteev bundle to flag variety. I'm sure you all have your own favorites, so this is one. Now, how does it work? So so if you have this Q variety, right, you have this nodes. Well, people, I think in this workshop, I don't have to read what the Q variety is, but just yes, we have those nodes. We call them gauge nodes, right? V1 to Vn-1, so those are the ranks of those groups, right? So you have unitary groups, U of Vi, to take the product of them, and this vector of V, it encodes the weight of the representation of the spin chain. So this is what it would be like spin chain SLN. So so think of this as a Dynkin diagram of the Lie algebra, right? And this would be SLN with certain choice of the representation, and then those beta roots will live in a maximal torus, right, of G. Sort of think of them in complexified form. So it's GC. And then remember we had an integral. So by integrating over x, what we're doing, we're effectively projecting out on well-invariant combinations of beta vectors, beta roots, right? So if you think about beta nuts equations, you studied them for a while, but you can ask, well, say you have a beta equation, you solve it, you find one solution, x1 equals something, x2 equals something, and so on. Now, if you think about it, it doesn't make much sense, right? Because there's a while group presentation, so like individual beta roots, they do not tell you much. Rather, what you should be looking at are certain while invariant symmetric combinations of those groups, like say elementary symmetric functions, so there's like a product of them, sum of them, stuff like this. And this construction effectively does this for you. And there's a flavor group, which comes from framing, right? And its maximal torus gives us the parameters of an A, right? And then there's also the fundamental matter, which sort of provides the homes from VI to J. So, and then we want to study quantum deformation. So again, so Andre and Richard reviewed this, so I'm going to go quick here. So, what's a variety? So variety is essentially it's the certain linear algebra data, which formed by those meta fields, modeled out by the gauge, roughly speaking, and then X becomes a module of a quantum group in Hierarchos correspondence construction, right? Of certain Nakajima and Nakajima correspondence. So what you need to do, you need to look at the compute integrals in equivalent K-theory of space of quasi-maps from some curve, in our case the curve of gene 0 into X, which is weighted by this new variable Z. So those will be eventually twists in the quantum mechanical system, which is subject to the additional covariant action on the base curve. Right, and then just maybe we can go over a couple of slides quicker. So say you can take a quill variety. So the way it's defined, you take a moment map, which is mapped from T star of space of quill representations to the dual of the Lie algebra G. So T star, because kind of you double all the arrows. And then the quill variety is a certain quotient of the preimage of the 0 on this moment map in the presence of certain stability conditions. Right, so Andrew reviewed them, so then I'm going to comment this later. But that's kind of in terms of, or you should think of it as a certain stack quotient of the semi-stable locus over G. So maximal torus here is the maximal torus of the automorphism group of the quiver. And just to give you an example, so if you take a quiver which is potential bundle to the Grassmannian of K hyperplanes in Cn, and then it you take the tautological bundle B of rank K, right? Then so the classical K theory of the space will be simply formed by tensorial polynomials of this W, this V, and W, which is a trivial bundle, and their duals, right? So for instance, if you take this class here, which is V squared minus lambda cubed V dual, then you can write this polynomial in terms of Chern. Any questions so far? And then, so the quantum deformation goes the following way. So we have this, we define a quasi-map by the following sets of data. So there's this vector bundles script VI, curly VI, script VI and WI, which essentially has to lift from, like, pull back from of bundles VI and WI to the moduli space, right? And then sort of such that this section here satisfies the condition mu is equal to 0, right? So the curly M is just the sort of linear algebra data that is sort of taken from the quiver, right? And essentially you're looking at the pre-quotient, right? So kind of you sort of integrate, and so what we're going to do, we want to kind of integrate over this modular space of this maps before instead of taking the quotient over G. Right, and then there's a whole construction here. I don't want to review much of it. It's essentially we define an evaluation map to this quotient stack, and then quill variety itself is a certain open subset, and then depending on which point on the curve you pick, that you can be either inside X or it can be outside of X, right? And if it's not inside X, then it's sort of have singularity, and then there's a whole procedure of how to remove them by attaching this rigid P1s until the kind of the endpoint of this P1 becomes non-singular. So if we change those bundles VI and vary the polynomials F with different degrees, right? So we get the moduli space, which we're going to note as QMT of X. Right? So for fixed degree, if you change the coefficients of F, right, and we change the bundle, we're going to get the moduli space. And then, well, there's a certain, again, whole machinery of how to define it, and it was done, well, in many papers before ours, right? So you want to, well, define a certain quantum class, which is the sum over the quasi-maps of 4 degrees of certain contribution. So if you have your class tau, right, you can compute its sort of quantum counterpart by sort of taking its tensoring with the virtual structure sheaf on the moduli space and with this quasi-map stack of assuming certain non-singular conditions at infinity, so between this infinity here. So there's a certain case-rated push-forward calculation. and then multiply it by those variables z to the power d, and then take the sum over d. So it's going to be a certain series in z with the rational coefficients of equivariant parameters. So, and then we can show that if you define those quantum classes in this way, they form an algebra, they form a ring, right? So it's a commutative associative unital algebra, and the unit here is non-trivial, so the unit element in algebra is not equal to 1, right? It's a certain series like this, right? Okay, so let's do an example. So the favorite function from everybody in this room, I guess, right? So Q hypergeometric function. So if you take the, if you equivariate this cotangent bundle to CP1, right, then there are two fixed points of the maximum torus, we call them sort of, and then there are two equivariant parameters, and there's one scalar parameter z, which is the quantum parameter of this quantum information, right? And then the, so this quantum class for 1, if you just compute the, what's called the vertex function, like uncapped vertex function, is a certain series in z, right? And the coefficients are ratio of this Q factorial, right? Which in this case amounts to be equal to the 2 phi 1.
So d is positive. Usually in the 2 phi 1, d is greater equal to 0.
What?
Isn't it? There should be a constant term in the 2 phi 1.
Oh yeah, greater equal than 0. Yeah, right. Yeah, thank you. I think it might be just, it's not showing. I think I see it in my slides. Yeah, right. It starts with 1. Yeah, that's right. So the, then the parameter h bar here, it has the meaning of it scales to cotangent direction on the curve, right? So we have so CP1, there's a scalar, the first term class with the scalar parameter at z, right? And then there's the dilation parameter of the fibers. We can multiply it by the constant. Right. And then, well, again, we've seen this before. I'm just going to say it again because, well, I proved part of it, right? So this vertex function as a function of the equivariant parameter and the scalar parameter is when you multiply it by something, you multiply it by some ratio of factorials, is an eigenfunction of the trigonometric coordinate Schneider Hamiltonians, right? And as we mentioned before, there are in fact two families of Hamiltonians, right? One of them shifts the equivariant parameters, another one shifts the scalar parameters, right? And there's a relationship between these two guys so if you swap A and Z, and in addition to that you invert the H bar, then you get the other guy. So it's a manifestation of so-called 3D linear symmetry. You can some another concept from physics. And then again, so Andrei mentioned this, but like the again, so it's something that we proved over here, that if you take this function, right, and then you would truncate it at certain lattice in Q and T, then the series, which has this kind of form, like, because you have those Q factorials here, once it vanishes, right, all higher terms will be 0 as well, right? So you're going to have a polynomial. And then sort of those polynomials that appear in the polynomial representations of the Abel-Haheki algebra and stuff like that. Okay, so now let's look at some aspects in more detail. So if you take the T star of the Grassmannian, then there's a following theorem that if you have the so you can define, so remember there's a Q, parameter Q that scales the base curve, right? And then if you take the quantum class and define it by the vertex function, so then the limit Q to 1 is well defined, so you get what is called the operator of quantum multiplication by the class, right? And its eigenvalues are given to classical expression for this class, right? So this polynomial tau of Chern classes, but instead of Chern classes, you need to substitute solutions of beta equations. So now basically, the structural levels of density are the same. It's the same kind of tautological guys that you had before, but now you need to solve beta equations for it. Right? So here, z. So notice that if you send z to 0, the right-hand side will disappear, and the you'll see that these symmetric functions of a's might be equal to 0. And then the equation provides you the quantum information of this construction. So again, so see, what does the answer depend on? It depends on the covariant parameters, on the twist, or the scalar parameter, and on the, well, in spin chain, so in spin chain language, those are called twist and the Planck's constant. That's why it's denoted with this bar in the first place. Okay, so this is very nice. And now the question is, what can we do about it? So how we can combine classical results and the classical integrable systems and quantum integrable systems sort of in one nice geometric setup. And this is what Opers come in. So first, let's write down the generating function. It's called Q. This is Baxter Q operator. It's a polynomial whose zeros are base roots, right? And then you can see that this is the eigenvalue of this quantum multiplication operators. If you expand it, you'll get the sum of wedge products of tautological bundle B, right? And operator of quantum multiplication by this class is this, right? The eigenvalue of this operator is this, where SI satisfies beta equation. Now, remember, so Andre mentioned stability parameter, right? So essentially, if you swap the chamber, right, then you should, instead of considering Grassmannian K in N, you should be looking at N minus K in N, right? So for the stability conditions to be satisfied. So let's look at both at the same time, right? So kind of leaving the realm of enumerative geometry, sort of, but kind of we're remembering it on the back of our minds as a motivation. So I want to look at all chambers at once, right? All stability, sort of the space of stability conditions, if you wish. So, but even that's without reference to stability conditions, so you have the Grassmannian and you have its dual, right? You have the kind of the flow. So, so let's say V check is the dual bundle to V, right? And then there's a short exact sequence like this, right? And now, so remember we have this Q operator for V, and we can define a similar Q operator called Q tilde for the dual, okay? And then you can check that if you, well, you can rewrite beta and Z's equations in terms of Q and Q tilde alone, right? And this is so-called QQ system. So it's a functional relation on this polynomial, on these two polynomials, Q and Q tilde, with the symmetric shifts, right? And there's a quantum parameter here and the equivariant parameter over there. So you can do it in general. You can take, say, you have a Lie algebra G of rank R, right? So Aij is the Cartan matrix of this Lie algebra of this root system, and this is how the QQ system would look like for in that case. So notice that, so on the left, so for every node of the derivative diagram, we have its own pair of polynomials. So here denote them plus and minus instead of Q and Q tilde. So there's a Q plus and Q minus. And then the right-hand side, you have the product over like neighboring nodes in the quiver, right? So if you have, say, SO8, like D4, there's a middle node and it talks to three guys, right? So then, which means that in this case, in the right-hand side, it will be the product of three Q matrices. So in the, from this point of view, polynomials Q plus, they contain beta roots. There's polynomials lambda on the right-hand side, they contain equivariant parameters. And those Q minus polynomials are auxiliary. But so in a sense, you should think of them as polynomials that correspond to this quiver varieties with different choice of stability conditions. And turns out that QQ system exists on its own. It's a very ubiquitous phenomenon in mathematics. So just to name a few appearances in the literature, so one of them we're going to describe today. Then, so people who study this, you can study the category of representations of quantum groups and then take its K group, K0, and then relations in this from the group, they also look like QQ system. Yeah, so the number 3 we'll be talking, so yeah, 1 and 3 I'm going to cover today. And then the last one, which is I'm working on right now, with a smear with Frankel and Anton Zeitlin, is that there's this interesting correspondence between difference equations, ODEs, and integrable systems, which is by Bazhanov, Lukyanov, Zamolodchikov, and turns out that this QQ system and Opers is a very adequate approach to study that. So ask me later if you want to know more about ODE I am. So turns out, yeah, and then like this object which I'm about to introduce, Opers or GQ Opers, is the key. Well, it's a very sort of it's the right thing, right guy for the job for all of these problems. So okay, so let's begin. So now let's talk about Opers. So first we need to define a Q connection. Okay, so this slide will first kind of abstract definition, and then I'll give you like a simple example. So take a arbitrary group. It doesn't have to be simple laced. Just you could take E8 if you want. Okay, G2 if you want. So and then take a principal vector bundle over P1, right? And then on the P1, I will be so if you pick some trivialization, I want to multiply my coordinate by Q. It's the same idea as before. It's like this maximal torus, the torus section on the P1. So call the separation M sub Q from P1 to P1 simply multiplies U by Q. And then I can consider pullback of my bundle under this Q multiplication. Right? So I can define Q connection, which is essentially like a linear map from FG to FGQ. Right? It's a section of the sheaf, but so think of it just as a matrix, right? And then if you change your trivialization, right, then your connection, this again, think of linear algebraically, just a matrix between linear transformation between two spaces. If you change bases, you need to do this, right? Only now, because it's a Q case, it looks a little bit unsymmetric. So like the gauge Q gauge transformations would look like, so you do G of QU, A G of Q inverse. Now, in order to reproduce it again, another calculus exercise for undergrads, show that you can get this one from so you need to scale Q and you need to scale A. Okay. Now, what's an Oper? Again, so Oper is a triple with a bundle with a connection and a reduction to the Borel subgroup. I'm going to call it B minus. So here A is a meromorphic G2 connection from the previous slide, and B minus is a reduction. Yeah, so it's a reduction of this bundle to the Borel, in SLN it's a lower triangular matrix. And now here comes the definition of the Oper condition. So it works like this. So if you take a modulus some subtleties with Zariski topology, so like you take U intersection with pre-image of U under this multiplication, right? So it's a certain Zariski open band set in U, such that the restriction of the connection of the Q connection to that set, right, takes values in this double Brioche cell. So it's a B minus, or so think of just essentially in the first order of magnitude, you can just ignore this. You basically think of this as B minus of C of D, right? So loop group for the Borel, and then here C is a Coxeter element, right? So if you have a wire group by G, you have product of reflections in some order, pick your favorite order of all reflections, and then compute the double Brioche cell for it. And so that's where the connection takes values in. Now, if you want to write it down locally, this is what it looks like. So it just simply says that so if alpha check are the alpha I check are Cartan elements of the algebra, and Si the reflections, so this is what it is. It's like product of some functions, phi I to the alpha I check, Si, and it's sandwiched between two elements from n minus. So that's the form of the connection. Okay, so if this was a little bit abstract, let me do the SL2 example. Now, let's G be SL2, and then instead of doing principal bundle, I can just take a vector bundle of rank 2. Now, so what's my SL2Q connection, right? So it's just 2 by 2 matrix, right? And then the Oper condition in this case would look like this. Like I only have one reflection, right? So the Y group is just a Z2, right? So there's an identity element and there's a reflection. So basically, if I have so you can think of I have a line sub bundle L, right? And then the condition will tell me that so the double Brioche cell condition will translate into the statement that if I act with A bar, which is the induced map on L, I will always get into the complement, right? So think about it this way. I have a two-dimensional vector space, there's a vector. Now you act in this vector with a matrix. What will happen? It will rotate, right? And then in general, but sometimes it may just stay the same, or sometimes it just can go to 0. But in general, you expect that it would go to the complement. Right, and this is what this condition is saying. So you can do two things. You can act on the vector. So S of u is the section of line bundle L. You can act on it with a matrix A of u, the Q connection, and you can do you can take the full back of the bundle. And the condition statement is that these two vectors are linearly independent. They are not parallel. Right? That's what the condition amounts to. But you can allow this to fail. This linear independence is allowed to fail at certain discrete points on. Well, here I took CP1 and I removed 0 and infinity, so you can take a look at the cylinder. So, and you can allow this to fail at some position points. I call them AL, and that should remind you the equivariant parameters from the numerative story, right? And then including some kind of tower of points on top of that. It's just some extra piece of data that I'd like to keep for myself. So that's one ingredient. And secondly, you want to add this twisting condition. So you would say that you would allow your Oper, your Q connection, to have a diagonal, have a gauge where the connection acts as a diagonal element. Right? So there's a gauge transformation G of U such that gauge transformed connection is diagonal. So now let's put this all together, right? So, say in some trivialization, the section of this line bundle looks like a vector of two. We call them Q plus and Q minus. For now, I just call them that, but you'll see in a second it's not an accident. And then say twist element has eigenvalues zeta and zeta inverse, right? And then the Q Oper condition is on the left. So this is a determinant of a 2x2 matrix, right? And A is diagonal, so it just acts with multiplication by this diagonal matrix over here. So after computing the 2x2 determinant, you get this left-hand side, right? And on the right, you get lambda of u, right? So you get this. So, and then that in turn is equivalent to the beta equations from the first half of the talk. And notice that the Q parameter here, right? So Q in the Q Oper plays the role of a G bar, that's the covariant parameter that scales the potassium fiber in the numerative construction. Questions? So it's rather simple object. It's a bundle with some reduction in the Borel, right? And then there's one more ingredient which is kind of not clearly seen in the rank 1 case, so which is called the Muir Oper. So now it's actually to make it work for real, we need to have, so we need to have four guys. We need to have bundle, connection, reduction to the Borel, so this flag of subbundles, and then there's another flag, which is called L hat. And this L hat must be preserved by the Q connection, right? So if this is the case, you can write your matrix as an upper triangular like that, right? And then and now you can, if this is the case, because of this condition, you can now diagonalize it by using gauge transformations from, I call them B, not from G of U, but from B plus of U, from the opposite Borel, right? So it's a stronger condition. So Muir condition gives you sort of narrow class of gauge transformations which you can use to diagonalize your Oper. So in this particular case, you take this element from B plus, and you just compute this, you're going to get the diagonal matrix. Yeah. Now, and also, often people talk about Opers or Q-Opers as different operators, and they are different operators, and this is why. So, again, take S as a section of the bundle, and then you can write every connection, a Q connection in this case, gives you the matrix difference equation, right? So, the Q shift of S is equal to A acting on S, and in this case, as a 2x2 matrix, you can write a scalar difference equation, right? So, double shift minus T of Q, single shift minus the rational function, and then so T of U is the eigenvalue of the transfer matrix of the x-axis. Now, how to recover? So that's a connection with a quantum XXZ model. How to get to a Rosner system? So for us, you do a very simple thing. Again, you write the Oper condition, right? And now I pick very simple polynomials Q plus and Q minus, both of them of degree 1, right? And so denote roots of those polynomials p plus and p minus respectively. Plug them in. You get quadratic polynomial on the left, quadratic polynomial on the right. Its coefficients are TRS commutative. Right? So this way you will get the Oper conditions on the nose equivalent to the spectral curve equation, right, for the TRS system.
The one type on the second term, the Q, maybe there's a Q too much. There's a Q, second Q.
Say again?
There might be a Q too much in the
Q too much?
in the numerator on the second term. Two Q's.
Oh, yeah. Okay. Yeah.
Which one is missing? Which one is too much?
Well, I guess this one, right? So it should be that combination. I constantly I change the formula and sometimes new errors come up. Other questions? Now, and then, so no, you can apply this reasoning to all other corners, other squares of the 3x3 table. So here, we show that this twisted Opers, they give you this, provide you this duality between XXZ and TRS. But then there's the, you can ask what about collider, what about XXX and stuff like that. So you can define similar objects in each corner. So far we're looking at like the first four, like top left four squares of the table. And in each square of the table you can introduce its own type of Oper. So for example, Oper which is relevant to the trigonometric collider is called twisted G epsilon Opers. I think Vitaly, with his collaborators, studied those a lot. And yeah, that gives you the duality between TCM and XXX. And then, well, there's a, well, we call them trigonometric twisted G Opers. I don't think anybody studied them before, but nevertheless, so they kind of gives you the duality between rational RS and trigonometric Gadan system. And essentially you can see that this is the, you have kind of this diamond, right? So like phase space of the TRS will be kind of, it's the product of you know, C stars, right, and X and P space, and then there's a reduction. You can basically send the, well, either C star C or C star. And then in the bottom you have rationally twisted G Opers, so original Opers that appeared in Franklin's work on geometric lengths, right, and Gadan model. So this is what they are. So green arrows, green dashed arrows is the manifestation of a 3D mirror image. Now, in general, so I gave you the SL2 example, the most simple one, but you can do it for any group G, right? So, and here's the theorem. So it's in this paper. So there's one-to-one correspondence between a set of non-degenerate Z-twisted Miura GQ Opers on P1 and a set of non-degenerate polynomial solutions of the QQ system for, and here we need to be careful, GL hat, not the other way around. Yeah, so this is the Q system for that Langland's dual root system. Yeah, and then, so you can see that non-degenerate appears twice. You have to be very careful when degenerations come, so that's kind of the whole story, but you can deal with it. At least like to understand what to do in type A. And then, yeah, so here's the kind of summary bubble representation of what's going on here. So you can relate the space of these Opers to many things that people discussed in this conference, right? So we have a QQ system, we have this many-body integrable systems, at least the type A. Then there's equivalent K-theory of Q varieties. And then, yeah, based on those equations, then here, we'll have like some time to talk about it. So there's a connection to, so it turns out that these QQ systems also arise in classical algebras. So there's some combinatorial construction by Fomin and Zelevinsky of generalized minors. And those generalized minors, they, depending on the root system that you're considering, they obey certain polynomial relations. Right, and I will talk about this a little bit. Maybe let's talk about this one first. Yeah, so if you have well, so first of all, let's do an example. Let's do an example, right? Now, you're probably familiar with this identity, which, well, my collaborator and I call Alice in Wonderland, right? It's like, you know, it's what it's just Nano, Jacobi, Trudy, or just Lewis Carroll for short. So you take a matrix, right? Computer's determinant, and then you can remove one row and one column. through a square matrix, you can compute that determinant. And then you remove another row in another column. And then you do it sort of in these different combinations. And it turns out that there's a quadratic relation on the determinants. Right? So, simple example, if you have 2x2 matrix, A, B, C, D, right, determinant is equal to AD minus BC. Right? It turns out that it's true if A, B, C, D are matrices, right? Only that you need to, in the right-hand side, you need to multiply by determinant of something else. Yeah, and then, so it turns out that if you write what's called Q, if this matrix is Q Wronskian, so it's formed by those Q polynomials, right? So you have Q, shifted Q, double shifted, triple shifted. Oh, no, sorry, no, never mind. You have to say Q, Q plus, so Q plus, Q minus, and then there are other Qs, which come from, well, the procedure which is called Backlund transformations. Let me leave it at that. So there's a canonical construction of how to write this Q-Wronskian matrix. And it turns out that this Alice in Wonderland identity is equivalent to the QP system for type A, and in turn to the XXZ beta equation. So this is how it looks like. But then it turns out that there's a generalization of this to any type. So if you take any group G, and then you would, well, we define first of all the principal minor. So say I have element little g from group G, right? You take its Cartan decomposition, and you look at the eigenvalue of the Cartan part, right? So its weight. So let omega be its weight, right? And then you say that if you take your Oper, right? You take your Q Oper, and let V of U be the gauge transformation that diagonalizes the Oper. Remember, for the mu Oper, we can take an element from the Borel, Q diagonalize it to the diagonal matrix. Question? Yeah. So let's call this polynomial Q plus of U. And then there are what is called generalized minors, which are obtained from the principal minor by acting on the right by acting on this with the two Weil group elements, right? There's two elements here, U and V. So think of them as kind of analogs of permuting rows and columns in the matrix. So if you swap, like the two columns in the matrix, it's as if you exit with the Weil reflection on those minors, right? And there's a similar construction in.
So you suppose that it is mutation?
Yeah.
Which
So
mutation?
it's an analog of mutation. So absolutely on the nose, it's mutations on the nose. So we call it, so in Opera world it's called Backlund transformation. So you start with this Q plus, and then as you act with Weil group, right? So then you have Q minus and then Q minus minus and so on. So like you have essentially columns of this matrix. So like all this tuple of Q functions in the general case, they are formed by orbits of the Weil group of the
So you do not specify graph.
Yeah, that's right.
Or,
Essentially, what you can do, you can just say that, I mean, essentially they all will be equivalent to that. So, okay, if you have the Denkin diagram from your Lie algebra, you stay in one node and then you mutate. Oh. And you mutate until you get to the end of Cox-Tailman, or Cox-Tailman divided by 2, right? Yeah, I'm about to hit. Yeah, right. So, yeah, so basically, yeah, so there's a direct connection between mutations and cluster literature and well, space of Opers, right? So basically, as you do the mutation, what you're effectively doing, you're changing the choice of the Borel subgroup, right? Now you're considering it with respect to different Borel, right? And then if you look at all possible Borels, you look at all spaces of all possible mu Opers. Yeah, and then essentially, yeah, there's a connection between space of Q Opers defined in this way and sort of space of solutions of this equation. Okay. Oops. Yeah, I should probably stop now. Yeah, like I had some questions before offline by some of you about connections with the Reisner system of higher end. So remember, if you take the now let's take the n flag, right? And then, well, you do the same thing, so that the components of the section will be the linear functions. You compute the Q Oper condition, And it gives you the trigonometric RS relations as I showed. But another comment I wanted to make here is that the momenta of the trigonometric RS system, those p's, they can be written as this ratio of few polynomials at the neighboring nodes. And well, turns out that from the point of view of enumerative geometry, it corresponds to multiplication by a certain class, right? Which is just the determinant bundle at node p multiplied by the determinant bundle at node p minus 1 dual, right? And so there's a very direct geometric interpretation of what trigonometric RS system is doing in that regard. Okay, and I think I should stop here. Thank you.
Any questions?
So I'm wondering then, would you be able to do like one variable for other types of root systems for one variable, like Ambien or F-type?
By it, you mean what? Opers? I can. Yes, Opers I can do it. But like the connection with the integrable system, so we did not, right, we did not do it, but in principle I don't see any issues with kind of this type of argument. Yes, if you write the Oper condition for say B-type or C-type, it has to be the algebra though. I cannot do like C checks here or something like this. Right, because it has to be an actual root system. It should be simple, simply connected to the algebra, LIGU, right? So for that I can define an Oper, and then like you should instead of this you're gonna get whatever Hamiltonian you want.
So you could do it for the exceptional cases as well.
Yeah, we could do that.
Thank you.
So like yeah, the G doesn't have to be simplaced, literally anything. Type independent statement.
What about the super?
We are working on it.
Thank you.
More questions?
Do you have elliptikerna någon gång vi hoppar?
Good. So I can tell you where we know the elliptic. In fact, we're writing a paper now with Anton and a student from Stony Brook. So so remember that the table of integrable systems has 9 boxes. I only have 4 here. So you can add 5 more, outside. So out of those, we know how to fill in 2. So we know how to do dual elliptic RS, right? And dual elliptic Calotter. So if you take elliptic Oper, like Oper on instead of Q-Oper, you'll take just Oper on the elliptic curve, and then run this program, you will get beta nuts equations and some integrable system, which is what's called dual elliptic coordinates. So that works. We don't have the construction for actual elliptic RS, and nor do we have a construction for del, but we think it should work eventually.
More questions?
So, speaking about the three-geometric line and this curve,
Yeah.
so is it possible to see like how it produces the classical one? So I understand the upper side, but the Q2.
So this is what it's called. Yeah. So this is called like Q angles, like Q angles at critical level. No, like so this is quantum Q angles. What again? I just went to like an object, right? And look at this kind of conformal blocks, right? This is that story at the critical level, right? So you have Q Opers and beta nuts like for the executive chain. So that's how it should be, right? Okay, so that's what they did, right? So this is a whole paper, right? So they have this correspondence between the quantum affine and this W from W algebra, right? And then if you kill one of the parameters, you'll get Opers. Thanks.
More questions? If not, let's thank the speaker. And we have a 15-minute break.
Yeah, sorry.
but I didn't understand the rules of really hard.